Naukowcy Pierre Agostini, Ferenc Krausz i Anne Lillier zdobyli Nagrodę Nobla w dziedzinie fizyki w 2023 roku za stworzenie ultrakrótkich impulsów światła, które mogą dać obraz zmian struktury elektronowej w atomach.
Ferenc Krausz is one of the three scientists of the moment. On Tuesday, he celebrated winning the Nobel Prize for Physics, which he shares with Pierre Agostini and Anne Lillier. The trio were awarded for creating ultra-short pulses of light that can expose changes within atoms. This could potentially lead to better detection of diseases. Krausz, after being embraced by loved ones, said he did not expect the accolade. The Nobel Academy said their studies had given humanity new tools for exploring the movement of electrons inside atoms and molecules, a phenomenon that has long been thought impossible to trace. And unsurprisingly so, changes in electrons happen in a few tenths of an attosecond. That's a time measurement so short that there are as many attoseconds in 1 second as there have been seconds since the beginning of the universe. The findings have potential applications in many different areas, one being a new in vitro diagnostic technique to detect characteristic molecular traces of diseases in blood samples. Lullier, who heard she'd won the prize while giving a lecture, described the next half hour as a bit difficult. She is the 5th woman to win a Nobel Physics Prize. The 3 laureates will share the $1 million prize.
I'm Ferenc Krausz. I'm director here at the Max Planck Institute of Quantum Optics and have chair of experimental physics at the Ludwig Maximilian University. Our main goal is to gain ever deeper insight into microscopic phenomena that profoundly affect our life. The key players in these phenomena are electrons. Electrons form the glue between the atoms that actually create the molecules of each and every living organism. Very seldom static. In most cases, our microscopic world is in motion. No matter how high the spatial resolution of a conventional microscope is, can such a microscope capture the dynamics that occur all the time in the microscopic world. To be able to freeze the motion of the fastest particles in our world, we need to be able to do microscopy in time. And that's exactly what we can do with short laser pulses. We are now entering the area where we are doing our attosecond photography of the microscopic world. Here you see 3 what we call attosecond beamlines, which are our high-speed cameras. If the exposure time of your camera is too long, then the fast-moving object will appear on your picture in a smeared way. In a conventional camera, you have a mechanical shutter which kind of opens and closes, or you can also do this electronically, but in any case you can't become much faster than a microsecond, about a millionth of a second, right? These are the fastest cameras which can actually even capture the motion of a bullet from a gun. Yeah? However, this technique cannot be developed much farther, and you have to come up with some new idea, and this new idea are flashes of light. Basically making very short flashes and illuminate the object you would like to capture, the motion of which one would like to capture, with a very short flash. And this is only possible with lasers. The trick to generate them is that actually we make the laser emit continuous waves at many different frequencies in such a way that at a certain instant in time the maximum of one of the oscillations of each of these waves of different frequency coincide. And that's the moment when correspondingly the sum of all these waves builds up to a very high intensity, and this is the peak of the pulse. I guess everyone has heard about the time unit nanosecond, which is a billionth of a second. Now, if we move towards shorter time scales, the first are the picoseconds, which are 1,000 times shorter than nanosecond. Then another 1,000 times shorter are coming the femtoseconds, and yet another 1,000 times shorter we move into the world of attoseconds. So 1 attosecond is actually a nanosecond, 1 billionth of a nanosecond.
And from our laser laboratory above us, the pulses are coming down through this evacuated tube, are directed into that very box over there, where we can decide which of these 3 beamlines is being served with these laser pulses, and which of the 3 beamlines is actually used for an experiment.
That's such a single cycle laser pulse. It has a strong enough electric field that it is able to rip off 1 electron from an atom. And this procedure of ripping off the electron requires the electric field to overcome a certain threshold. So if you now imagine this electric field in our short pulse has basically a single half cycle in the center, and then only a small fraction of this single half cycle delivers strong enough electric field for this process to activate. And therefore, this ripping of the electron can happen within a fraction of this half cycle of our laser pulse. And this fraction actually means a fraction of a femtosecond. So we indeed managed to generate in this way extreme ultraviolet flashes of light. Back in 2001, turned out to be 650 attoseconds. So the field of attosecond physics was born. Of course, we can't see the electron itself because it's that incredibly tiny. We can just measure the properties of the transmitted flash of light and the electrons with which this very short attosecond flash interacts leaves its imprint on the transmitted flash of light. So if we analyze this transmitted flash of attosecond light, we can learn about the instantaneous state of the electron at the very moment of the flash. Potentially, we should be able to boost the power of current computer technology by a factor of 100,000 approximately.
And this is our laser-based molecular fingerprinting instrument of the first generation. The system starts with a laser oscillator that generates a very short femtosecond duration laser pulses. And this laser pulse trans-illuminates our biological sample. In our current experiments, these are samples of human blood, human sera, or human plasma samples.
It's not so much the very composition that we are interested in, but more the change, because if we could measure changes in the molecular composition precisely and could bring it in correlation with changes in the physiology of the organism, then this might be a possible way of actually diagnosing a disease that is just about to emerge.
And here you see the heart of our molecular fingerprinting instrument of the next generation. As you see, it is much more compact than the instrument that is currently in use. It also offers a broader spectral coverage, so we will be able to measure a larger fraction of the molecular fingerprint, as well as offers higher sensitivity. And most importantly, it's going to be more user-friendly. So it's a first step towards clinical applications.